All right, I think we can get started. So hello, everyone, and welcome to this first seminar of the Clever Planet Spring 2022 seminar series. My name is Maxime Maurice. I'm a postdoc at Rice University, and that's my great pleasure to be your host for today's seminar. So those who were with us last semester might remember that we like to start all of our seminar with a little ritual where we say a few words about the Clever Planet project, as well as proceed to learn acknowledgement. So this semester we'll stick to this routine. So before introducing today's speaker, I'd like to remind you that I'm sorry, I have issue with the slides. Okay, I'd like to remind you that the Clever Planets project is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it is supported by NASA, and it is also one of the teams of the Nexus for Exoplanetary Science System Coordination Network under astrobiology. And as in the Clever Planet project, we're interested in habitability beyond Earth, but also in peaceful habitability of Earth itself. We find it very important to acknowledge that the research we do at Rice is pursued on the traditional land of several native people, namely the Karankawas and Sanas, as well as the Coahuiltecan, represented today by the Tapilam Coahuiltecan Nation, and the Aishaks, represented today by the Atacapa Aishak Nations. We see as our duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. And that's now my great pleasure to introduce today's speaker, Jacob Kegerreis. Jacob is a postdoctoral researcher at NASA Ames Research Centre. And before that, he did his master and PhD at Durham University, PhD on the topic of SPH simulation of giant impacts, for which he received the Springer Thesis Award. And he was then appointed as a short-term postdoc researcher at Durham as well. And he recently started late last year at NASA Ames Research Centre. He's going to be telling us about atmospheric erosion and more by giant impacts onto terrestrial planets today. And so with that, Jacob, the floor is yours. Take it away.
Okay, thanks very much. Let's see. Is that looking okay?
Yes.
Great. Okay. Yeah. Thank you for the invitation and introduction. I'm looking forward to chatting today about some of the projects I've worked on with colliding planets. I'm going to try and talk about perhaps too many different bits and pieces. The main topic that felt most relevant for this group is atmospheric erosion, looking at what these super violent events can do to an early atmosphere. But since that will be mostly based on these two, on these two papers that aren't that recent anymore, and some of you might even have heard me talk about them before at previous conferences, I thought I'd take this opportunity to also chat a bit more about the simulation work that's behind these projects, which I hope might be an interestingly different topic for some people to learn about, given the diversity of the group. And then lastly, I'll also present some brand new results from looking at the giant impact origin of the moon. So that's the general plan for this talk. I'll start by touching on why we're interested in giant impacts in general, plus how and why we use these big simulations to study them. It's also nice to spend a little more time on those numerical aspects because of the quite recent and still ongoing discovery of just how rather unexpectedly important the simulation resolution really is for the science that you get out of these very commonly used types of models. But I promise I'll make up for those more technical bits with plenty of pretty animations later on. Then we'll turn to atmospheric erosion and the scaling laws that we found for predicting how much atmosphere different types of impacts can eject. And then finally, we'll look at this alternate route for the origin of the moon that we recently found using more of these high resolution simulations. So to start with, giant impacts. Why do we care about these events in general? Well, our, I think, increasingly impressive understanding of planet formation in general is, in the simplest sense, this build-up from small objects into larger ones, which of course with amazing images like this one, we can actually start to be able to see happen right now around other stars. And for terrestrial planets especially, the final stage can be dominated by these dramatic collisions of protoplanets to build up the final planets that we see today. So it's no surprise that in our own solar system, we find lots of evidence of the consequences of different giant impacts. As just a few examples, Mercury's mantle is thought to have been partly stripped away by a late collision. Uranus was likely knocked over to spin on its side by an impactor even larger than the Earth. And probably most famously, our own moon, shown here for once in scale in astronomy to size and distance with the Earth, is thought to have formed following a late giant impact. Furthermore, we now have thousands of detected exoplanets, and as exciting as it's been to find out how common planets are, even more so they're amazingly diverse, including their atmospheres. This plot shows the densities of a handful of exoplanets with a wide range of implied atmosphere masses for the same total planet mass. Often that can be explained by the strength of radiation that they get from their star and so on, but sometimes not. And even in the same system, we can find two otherwise very similar planets with very different atmospheres. Since we expect giant impacts to play some significant role in planet formation anyway, a planet being lucky or unlucky in suffering a big collision that either does or doesn't remove its atmosphere might help to explain some of that diversity. Our own planet is also a compelling example, since we can both observe a life-supporting atmosphere that has survived to the present day and be confident that a giant impact took place late in its evolution to create the moon in the process. We know that the Earth's atmosphere has a complicated history of loss and growth via various mechanisms, as I'm sure many people here today know far better than me. But that's just one example of the observational evidence. The specific differences in volatile abundances compared with chondrites imply significant bulk fractionation, as would be caused by impacts, including small ones, rather than isotopic fractionation from thermal escape. So we'd really like to understand how much atmosphere different giant impacts can erode for all of these applications. Unfortunately, this isn't an easy problem to study. Atmospheres are obviously very low density compared with the rest of a planet, but that means that you'd need extremely high resolution if you're going to model everything at once numerically. Maybe in the future, we'll actually get to see a collision between exoplanets happen live. But in the meantime, since we don't have quite enough budget to build full-size planets in the lab and actually smash them together to see what really happens, simulations are about the best we can do. And because of that resolution challenge, most previous work has been focused on one-dimensional simulations and analytical simplifications, or alternatively looking at much thicker atmospheres that can be resolved, often also limited to only head-on impacts. But for example, people have estimated the propagation of a shockwave from an impact by treating it like a point mass explosion, plus a few other assumptions, which lets you estimate the ground speed all around the planet that's caused by that shockwave for a head-on impact. Then you can use a one-dimensional model to see how much atmosphere gets lost locally from that shockwave kick up through the ground. But this leaves a lot of unanswered questions about the more realistic and messy giant impacts that you expect in reality in 3 dimensions. So we'd really like to be able to model these events in full. For giant impacts in general, by far the most common simulation method used is SPH, standing for smoothed particle hydrodynamics, which is used in a great number of different fields and applications. And it's particularly good for this kind of dramatic and messy event without lots of nice symmetries. I know it's yet another 3-letter acronym in science, but at least this time SPH is a fairly descriptive one. We're representing our materials using lots of tiny particles, solving the standard equations of hydrodynamics and gravity too, in this case. And to solve the proper fluid equations, rather than just modeling little balls bouncing off each other, each particle smooths over its closest 50 or so neighbors, as tried to indicate here, to calculate the density and other properties. With that framework in place, we simply have the computer calculate the forces between all of these many different particles, update their velocities and positions, and then repeat that over many short time steps to see how the planets evolve. The more of these particles we have, then the higher the resolution we get. As some quick historical context, I suppose, for the modern simulations that you'll see later, SPH was first used to look at giant impacts really quite early on in its development. At that time, we're looking at only about 1,000 particles in total, given the computational constraints that they had, but still that was enough to get a proper handle on the giant impact hypothesis for moon formation, since spurred on so much work and progress. Oh, this is a good time as well to clarify that both this and all of the other SPH simulations that I'll show later are fully three-dimensional. We're just looking at a cross-section of the particles for these snapshot pictures. Jumping forwards then about 4 decades to today, most papers coming out in the last couple of years are using about 10 to the 5 up to 10 to the 6 particles. But that actually represents only a pretty mild improvement since the early 2000s. And furthermore, that kind of resolution really isn't enough to look at something like a thin atmosphere. So we still need some big improvements. And that brings us to supercomputers. This is the one that we have in Durham that we get to use, as well as people internationally get to use as well. And I'll talk a little bit about what actually needs to go on inside supercomputers to really bump up those numbers of particles and thus open up new science topics that we can tackle. For anyone not familiar, a supercomputer is really quite genuinely just lots of normal computers hooked up together. The individual processors aren't even really that much faster than in a normal laptop. It's all about using lots of these cores at once in parallel to speed up the calculations. On that note, pretty much every laptop itself nowadays is a supercomputer, as you can tell every time they advertise things having a quad-core CPU or whatever it might be. But anyway, within a normal supercomputer, we have hundreds of so-called nodes, each of which will have a few tens of cores, and each of those cores can do its own calculations. These machines as a whole are enormous, so both for the budgetary and environmental impact, and of course getting the better science results, people spend a lot of effort to try and use them efficiently. But that's also easier said than done. And something like an SPH simulation of a giant impact is in some ways a particularly tricky example. We have a huge number of particles and lots of calculations to do for every one of those, every single time step. The typical approach, which does work okay, is to divide up those calculations between our supercomputer cores simply by chopping up the space in something like this. The problem is that different particles and different spatial regions will have very different amounts of work for the computer to do. So for example, this core here might finish that boring part of the simulation very quickly and will then simply be sitting there idle and wasting time while it waits for this core to finish the much harder work it has to do for that complicated part of the simulation. So about 6 years ago now, shortly before I got to join in as my PhD, a small group at Durham in the UK decided to try making a really big fresh start to this situation to try and improve things. And this has become a really nice collaboration between actual computer scientists who understand this stuff far better than any of us do, and astronomers. Most of those astronomers were cosmologists before we started butting in with all our planetary applications. But for me, it's been a really nice way to learn far more about what really goes on in these codes and supercomputers than I would have otherwise. The code that we've developed, called Swift, is also fully open source with lots of examples and so on. So please feel free to have a look and even ask us for direct support if you're interested and need it. But the biggest approach that we have is to make sure that the work is shared out across the supercomputer instead of simply the data or the spatial regions. And this so-called task-based parallelism, we have the code generate a long list really of all of the calculations that need to be done every time step. then each core of the supercomputer can just go and grab a task from that list, work on it however long it takes, and then when it's done, it will just go back and grab a new one. This way, we're never sitting and waiting for the other parts of the supercomputer to finish, even if those different individual tasks take very different times to complete. There are a bunch of other helpful things going on inside Swift that also speed things up, but I think for time, I should skip them. But I at least was pleasantly surprised to find how far more understandable and tangible those improvements are than I'd expected. So I'm happy to talk about those if people want to. But what that really means is that we can now run simulations with hundreds to thousands of times higher resolution than before. It's about time I show some animations to celebrate making it through that numerical background. So for comparison with the 10 to the 5 particle images that you saw before, here now is a 10 to the 8 particle simulation of a giant impact onto Uranus. Colored on the left, we've got the materials, and on the right is the thermal energy inside. But this gives you just a nice idea of how cataclysmic these events can be for the planet on the receiving end. So making those pretty pictures and animations is great, and who knows, maybe that's already enough reason to do all of the numerical work. But there are also some probably slightly better scientific reasons for bumping up this resolution as well. As an analogy, much like building a larger telescope, we can either zoom in to study the same things that we've looked at before, but now in great new detail, or we can also look for the first time at completely new topics that we couldn't resolve before, such as including a thin atmosphere on a planet. But perhaps even more importantly, we can actually now test for the first time whether all of the previous results we've had from lower resolutions were reliable and numerically converged in the first place. Of course, there are plenty of not fully realistic assumptions in SPH and any other model, but before you even think about those issues, you first need to worry about whether the model itself is converged and being calculated properly for anything numerical. For example, in this example of Uranus, we were surprised to find that even a large-scale result like the rotation rate of the entire planet is significantly unconverged at standard resolutions. And even there, you need at least 10 to the 7 particles to start getting it right, contrary to what we might have originally hoped for if it had been only small-scale details that needed higher resolutions. Oh, incidentally, this project also gave us the most I suppose, interesting headlines that we've ever had, but I guess that's just to be expected when studying that particular planet in the solar system. But that's enough about the numerical background. I think I'm doing okay for time. So that will bring us to the second topic for today of atmospheres and eroding them. So armed with these new high resolutions across those 2 projects I briefly mentioned at the start, we simulated a whole bunch of different giant impact scenarios, changing the speed and angle as well as the masses and compositions of the bodies, aiming to cover a really wide range of the relevant parameter space for even broadly terrestrial planets. Overall, we hope to find out how much atmosphere gets removed. For example, perhaps even a smallish collision could blast away all the atmosphere, or at the other extreme, even a big one might still let some atmosphere survive, who knows. And then we could look at mechanically how the atmosphere is actually eroded, which I think I'll only briefly touch on today. And finally, see if we can then put all of that together to make general predictions for any such collision in that regime. To give you a quick taste of what we found, here are some more animations of scenarios with a roughly Mars mass impactor about to hit a roughly Earth mass target with a 1% mass atmosphere. So this is still far thicker than the present day, but not nearly thick enough to start cushioning the impact. So as with Uranus, you can see how much the entire planet is getting disrupted with these big shock waves getting sent out and oscillations and re-impacting debris. And then on the right, we have some higher speed impacts where a lot more material is eroded. And we actually tested all the way up to extremely fast collisions where not just the atmosphere, but absolutely everything gets obliterated. So a diverse range of outcomes. We then started by looking into the different mechanisms by which different impacts actually eject the atmosphere. I guess most obviously, local material will get directly blasted out of the way by the impactor plowing through. And then both the big shock waves and those violent oscillations that you saw can eject material globally. Plus the secondary impact of any large fragments that survive contact can erode more material when they fall back. And then on the bottom here are some cross sections highlighting the particles in purple that will be eroded by two example impacts, from a highly grazing collision on the left to a much faster head-on one that ejects a whole load of mantle as well as the atmosphere too. I should also emphasize that this is talking about the immediate removal of atmosphere. There could well be additional longer-term loss that's initiated by a giant impact, for example, via the heating that it brings, leading to later hydrodynamic escape. But this is looking at what immediately gets blasted unbound from the system. So if we now step back to look at how the total erosion changes across these different impact scenarios, here we have the fraction of lost atmosphere, so 1 meaning total loss and 0 no loss, for a subset of the simulations of the same base scenario, changing only the angle or only the speed. So here are sets of slow, medium, and fast impacts at different angles from head-on up to highly grazing. And the first unsurprising conclusion is that the angle makes a really big difference. We found that the overall angle dependence is matched pretty well by a quite simple geometric estimate for the fraction of mass of the two bodies that interacts, as I'm indicating down here. But we have some complicated effects as well once we start to look at the details. On the right now is sets changing just the speed for head-on impacts in blue, or more grazing ones, well, mid-angle ones in orange. Unsurprisingly, again, the faster the impact, the more erosion that you get. But the amount that matters depends strongly on the angle. Some previous studies had actually concluded that giant impacts would almost always remove either almost none down here or all of the atmosphere, because they'd only looked at head-on collisions. But clearly with other angles, it's very possible to lose half an atmosphere or any other fraction. Speaking of previous models, these circles here come from taking the ground speeds from our 3D simulations and then ignoring our actual atmospheres, using those one-dimensional predictions for local loss given those simulated ground speeds. And they match pretty well in most cases. On the other hand, these crosses show the results from using the estimated ground speeds from those simplified shockwave models, which unfortunately tend to significantly underestimate the erosion, in addition to being limited to only head-on scenarios. The next most important parameters after the angle and speed are the masses, of the target and impactor. So here each color is showing the same set of angle and speed scenarios where only the impactor mass is changing. And the different line styles are for different target masses. So we immediately see that this is really independent of the total mass for the same ratio of impactor to total mass. And across the different angles and speeds, we get really quite a ubiquitous trend of increased loss as the impactor gets larger. Now these blue scenarios that I've added in are from slow head-on collisions, which we found to be interestingly chaotic for the atmospheric erosion. Mostly because, as you might remember from the animations, excuse me, I'm talking too quickly. As you might remember, we see a lot of material getting briefly ejected and then falling back, kind of like when you drop a stone into a pond. So even for our higher resolutions, the precise way in which that material falls back and ejects more atmosphere is very sensitive. So rerunning the simulation with just slightly different initial conditions can give somewhat different results for these chaotic scenarios. But then finally, these yellow lines show targets and impactors made entirely of iron or entirely of rock. So highly different compositions to the roughly Earth-like cores and mantles that the others have. But nonetheless, we still find the same quite neat trend with the impactor mass. So putting that all together, here now is the scaling law that we found can really quite neatly predict the erosion from any impact across this wide range of scenarios as a power law over these pretty expected parameters. I made this slide at the end of the original long lockdown, so past Jacob decided it'd be a great idea to make up for equations on slides by adding some silly graphics. But that aside, as we saw earlier, the collisions we simulated cover this full range from very little up to total loss of atmosphere and everything in between. And this project was focused on getting these direct results rather than all of their applications. But this scaling law can, for example, be incorporated into wider models of planet formation or be considered with specific examples like the moon forming impact. So here I've stuck on 5 of the currently considered scenarios for plausible moon forming collisions, and they range from about 10 to 60% lost. So as our understanding of the history of Earth's atmosphere improves, this might also be a new way to constrain different impact hypotheses, or at least to help us account for their possible consequences. To add some more numbers, these are the rough parameter ranges that we tested. Though since we don't see any deviation from the trends at the extreme values, it's plausible that the scaling law still applies at least some ways beyond these ranges. Though as, for example, you get down to much smaller crater-forming impactors, you'd certainly see a change to that different regime. 2 relevant parameters that we did test with a few simulations, but not yet enough to fully incorporate into the scaling law, are the initial atmosphere mass and its temperature. Both of these do matter a little bit, but not very much compared with the rest. So a significantly thinner or a significantly warmer atmosphere does see some more loss, but not a huge amount. Other limitations that we should be thinking about for the future are what happens to the atmosphere afterwards, as I mentioned before, or if a planet has a widespread ocean, then that could actually increase the immediate loss of atmosphere, perhaps even up to a factor of 2. One final aside for this topic that we also looked at for the first time is what happens if the impactor has its own atmosphere as well as the target. We found this makes little difference to how much of the target's own atmosphere gets ejected, but for slow impacts, much of both bodies' atmospheres can survive. So the impactor actually builds up and increases the total atmosphere mass on the final planet. However, it's then important to remember that the impactor will also donate most of its core and mantle material, so the fractional mass of the atmosphere always goes down compared with the mantle and core mass. But it's an interesting point in terms of the potential composition changes that a volatile-rich impactor could bring to the atmosphere, in addition to the overall change in mass, as I'm indicating there. So that brings us to the final and newer topic for today about the origin of the moon. As some very quick background, for quite a long time, people really weren't sure what the moon was made of or where it came from. And of course, a lot of the weirder ideas were ruled out during the Apollo program, if not even before. But I did enjoy finding this paper comparing the seismic properties of Apollo moon rock samples with different Earth cheeses. So who knows? But we're now pretty sure that some kind of giant impact did make the moon. So what do we actually observe about the moon that those models are trying to explain? Well, most straightforwardly, the moon is very large and carries a lot of angular momentum in its orbit compared with other planetary systems. It's got a tiny iron core, a fairly thin crust, and is highly depleted in volatile elements. Perhaps more surprisingly, the isotopic ratios in lunar rocks are extremely similar to the Earth for many elements. There are also extra mysteries like the moon's slightly more non-spherical shape than expected from current tides and its inclined orbit away from the Earth's equator. I couldn't find any sensible pictures for those, so here are silly ones instead. And the so-called canonical giant impact model with a Mars-sized impactor hitting the Earth, not that different from the atmosphere simulations you saw me show earlier, does a really good job to explain the mass, the angular momentum, the iron content and volatiles of the moon. However, it makes a debris disk of almost entirely impactor material with not very much excavated from the proto-Earth. So when the moon later accretes from that debris disk, it wouldn't match the Earth's isotopic composition, unless the impactor already had a matching composition too. But there is some debate for how plausible that may or may not be as an option itself. Somewhat similarly, the fossil figure and inclined orbit might be producible as the moon's orbit evolves through resonances and other third body interactions, for example. But returning to the isotopic composition, the relative difference between the post-impact moon, oh, sorry, I meant to advance the slides earlier for what the canonical model is good at explaining. But for the isotopic compositions, we tend to measure this using this delta ft parameter, where each ft in that equation is the fraction of each silicate reservoir that originated from the target. So a delta ft close to 0 indicates a very similar moon and Earth composition, while a highly negative delta ft, like the minus 70% that canonical models produce, indicates a very impactor-rich moon with not much Earth material. So driven by this isotopic concern, amongst other things, a whole bunch of alternate impact scenarios have been proposed to try to increase that delta ft and other observations about the moon, primarily by trying to mix more proto-Earth material out into the debris disk. You could, for example, have a hit and run impact where most of the impactor escapes. Try having multiple impacts after each other to build up combining moonlets over time. Or perhaps most promisingly recently, allow a much higher energy and higher angular momentum impact with a very large impactor or a rapidly spinning proto-Earth, though exactly how easily or not that excess angular momentum could be removed later is somewhat of an ongoing debate and discussion. So there are a bunch of apparent ups and possible downsides like that to all of these hypotheses, but suffice for now to say that we aren't yet certain how the moon formed. So we're keen to continue both studying all of the implications and constraints for these options, while also searching for other possible alternatives. Which brings me to our recent project, where prompted by some very brief tests we did for a methodology paper last year, we started looking at canonical-like impacts using much higher resolutions, not really being sure what we might find. But what we found was a change with resolution even more striking than in the Uranus case, where at high resolutions, a separated satellite consistently forms immediately after the start of the impact. Again, adding some new concerns for these previous models that weren't able to test their convergence like we now can. The more exciting part, though, is what happens next for that satellite. So here I've colored in purple the particles that will end up in the satellite, and in green for those ending up in that inner remnant. And as the body separates, the inner remnant torques it forwards, transferring angular momentum outwards and slingshotting it onto a much wider orbit. To see that in motion, here now is a 3D animation of the simulation data, following a fun time I had playing around with rendering things in Houdini. I guess I should say quickly that everything here is still controlled by the SPH simulation particle properties, but the exact mapping of opacity and emission, etc., are somewhat arbitrary, since what this would probably look like in reality is just a massive opaque cloud after the first second. So here we see that satellite starting to form and getting slingshotted out into this wider orbit. And as that inner remnant falls back and sprays out into a smallish debris disk, everything calms down a little bit, and we end up with our stable circular satellite. It's certainly nice to get a bit more perspective of these and these cross-section simulation animations that we've been able to look at before. I need to get sound effects on these as well. Okay, so the resulting satellite that we actually get is on an almost circular orbit with a mass very similar to the moon. Other impact scenarios with different angles and speeds give us satellites with a range of slightly larger and smaller masses. and a high periapsis, way outside the Roche limit, so safe from being tidally disrupted later. But for some impact scenarios, as we change the angle and speed, that initial torque from the remnant onto the satellite might not be quite enough to place it immediately onto a stable orbit. So here we see a satellite that was formed in a similar way, but is actually falling down inside the Roche limit. However, not only can a large fraction of the satellite survive the partial disruption, the stripped material can again torque that satellite outwards, raising that initially low periapsis out onto a now wider and safer orbit. So this really extends the range of scenarios that can actually make a stable final satellite. I've got an animation of this too, and I think we maybe have enough time. I might cut off the end, but here we'll get to see a bit more of the impact from a different angle, and the that inner remnant falling back to re-impact the planet in a minute here. And I'll actually just skip forwards a bit to where we can see the tidal stripping as the satellite falls too close and it starts getting launched out onto that wider final orbit. But I think I'd better move on for the sake of time. So if we step back now from those specific examples to the wider suite of impact scenarios, we find this whole range of satellites with initial periapses, both in and outside the Roche limit, that then suffer different amounts of tidal disruption. For me personally, I think this was really the most interesting part of the project, even if it weren't to have any connection with the origin of the moon. For the subset of satellites that do get partially tidally stripped, here you can see their initial masses and periapses as the diamonds, connected then to their final values as the circles. So there's a huge variety of initial states, but in every case of significant mass loss, the periapsis gets raised, often to well beyond the Roche limit of about 2.9 Earth radii. I'll skip over the details for now, but in spite of the diverse initial masses, debris environments, and sometimes even quite rapid spins, we find that a very simple analytical estimate is actually a decent prediction for how much mass is getting stripped away in these cases. It's important to note that, of course, not every giant impact can make a satellite in this way. If the impact angle starts to get too low, then you don't get enough torque from the inner remnant to launch out that satellite into a survivable orbit. But if the impact angle then gets too high on the other side, then the satellite doesn't fully separate itself from the remnant and falls back in. However, we did find that having a spinning target and or a spinning impactor before the impact can significantly extend the range of viable angles for satellite formation. So that helps us to not be restricted to any overly fine-tuned or low likelihood part of the whole parameter space. When we look inside these satellites now, since we have the resolution to do so, we find an encouragingly moon-like low mass of iron and a somewhat higher than canonical, but still not huge bulk composition of proto-Earth material. However, the distribution of that proto-Earth material consistently shows a strong gradient with radius. And we find that these satellites have more highly proto-Earth rich outer layers, by which I mean a significant proportion of the mass, over a more impactor rich deep interior. We might quickly get beyond the scope of this project itself, but it's tempting to then speculate about whether these otherwise rather compellingly moon-like satellites could also help to explain the isotopic similarity of the Earth and Moon. Not only do we have quite little information about the composition of the lunar interior, some recent analysis actually suggests that the inner moon looks a bit less like the Earth than the exterior, though it's a complicated topic. And speaking of complicated topics, we might expect a compositional gradient like this to mix itself somewhat within the magma ocean. But depending on the impact scenario, the interiors that we find for these immediate satellites can be fully molten, subliquidus, partial melts, or even solid, compared with the typically only fully molten moons that you would expect from the other disk accretion scenarios. That option of a slightly shallower initial magma ocean for the moon might also be helpful for explaining the thinner crust. And two other considerations that have been quite recently suggested to help even the standard canonical model explain compositions without the extra proto-Earth that we find here are one, how a pre-impact magma ocean on the Earth might be more easily mixed into orbit, and two, how a glancing hit and run impactor that then returns later for the final impact could both provide a higher likelihood way to get the correct scenario for speed and angle that we need in these scenarios, and also lessens the amount of mixing that you need in that final impact. So depending on how much the composition gradient does or doesn't survive, and whether any of these other options could also help, we end up with a delta FT ranging from an already pretty encouraging -40% right up to -10%, which could satisfy the isotopic constraints for a really decent range of impactor compositions. One other implication of these results is that the moon could have started on a much wider and optionally also eccentric orbit compared with the circular and much closer in satellites that accrete from a debris disk or a synestia. This opens up some new options for the subsequent orbital evolution that is currently the source of ongoing discussions for how easily or not things like the fossil figure and the inclination could be explained. But to be clear, while I think that giant impacts can certainly produce immediate satellites like this, I'm of course not claiming that this has to be the only explanation for how our moon formed. It was an exciting surprise for us to find these stable satellites suddenly appearing with sufficient resolution, with the right moon-like mass and ion content and angular momentum, and these even more Earth-like compositions. But just like for all of the other current ideas for how the moon might have formed, there's a huge number of open questions, ranging from pre-impact topics like the possible compositions for the impactor or the expected spins and impact speeds of the planets, to many post-impact topics like the evolution of magma oceans and the satellite's orbit and tidal evolution. And lastly, of course, there's all of the present-day sample analysis and geochemical work to better understand all of the constraints that these models need to explain. So I think we could look forward to continued efforts to try and constrain the likelihoods for all of these different scenarios. And in the meantime, there's plenty to keep pushing with numerical pieces of the puzzle, from improving the equations of state we have that control how the materials behave, through to exploring even more new parts of the parameter space with these high resolutions that we can now play with. And with that, I've reached the end of this rather dense and somewhat meandering talk. So as a very quick summary, after diving into some of the details about how we try to make the most of supercomputers to increase the resolution of our simulations, I showed how different giant impacts can have a diverse range of outcomes for a terrestrial planet and its atmosphere, but that we can still use a quite neat scaling law to predict the erosion from any such collision. Focusing on the Earth, that means that different options for moon-forming impacts cover a quite wide range, of possible atmospheric losses, but are unlikely to remove the entire atmosphere in one go. In addition to enabling new topics like that, we found that these high resolutions reveal an alternate and simpler option for the origin of the moon without needing slow accretion from a disk, with categorically different results to the unconverged outcomes from standard resolutions. It's also another example that reinforces how crucial those tests for convergence can be, like the Uranus results as well. These immediate satellites on wide orbits have some compelling similarities with the moon, but there are lots of open questions left to answer. And speaking of open questions, thank you all again for listening, and I'll be happy to answer any.
Well, thank you very much, Jacob. I'm clapping on behalf of all the audience for this great talk. I'm sure we're all mesmerized by your great animations, and so
no one needs to listen to anything else. We got the pretty pictures, and that's enough.
Yeah, no, that was really interesting. So I didn't explain that before you talk, but if you have questions, please raise your virtual hand, and if you're attendee, I will allow you to talk, or please also raise your virtual hand, even if you're a panelist. That will ease the flow of question. You can also write down your questions in the Q&A section. And I think we have a first question from Madeline. So Madeline, you can talk. Although I think you have to unmute yourself.
I'll be right back as well.
All right, well, waiting for Madeline, I guess we can take Tom's question.
Hello. I think our speaker stepped out for a second.
Oh no, I'm back.
Oh, sorry. Yeah.
Literally a second.
So really fascinating simulations there. I mean, there's a lot of potential in all that. Clearly, I mean, I was just wondering about, so then these moon forming scenarios that you were investigating. You kind of answered the question, but I was wondering in there, you know, whether the temperatures always remain high enough in those stages that everything is magma, or do you start crystallizing, get cool enough that things are crystallizing, and how that affects how the process that go on during that, during the whole thing in the scenario. And you mentioned something about maybe there could be some crystalline cores and lower mantles forming, but I'm just wondering if you could maybe say a little bit more about that, or if you know anything about that.
Yeah, of course. No, it's a very good question. And yeah, I'm aware how much I skimmed over some of these details. So I guess I'll actually open with a caveat that while we are able to track and investigate all of these things with these simulations, it is a case where we're somewhat reliant on these equations of state, which, especially when you're trying to look at phase transitions and things like that, are starting to get there, but there's definitely some uncertainty in that. But in terms of the general temperature evolution, then yeah, for sure, a large amount of the material is highly shocked and gets up to easily 4,000 or 5,000 Kelvin or so. But what we're finding in these simulations, compared with the more normal disk and synestia forming things where everything's highly mixed and molten, is that the deeper interiors, which is also basically why they're more impactor rich, can stay almost cohesive throughout the impact. And they get somewhat shocked, but they stay relatively close to their initial temperatures. So if you start with a cool planet and have the right impact scenario, then you can have a near solidus or liquidus interior to the moon from what we're finding in these scenarios. I certainly don't have the expertise or perspective to say exactly what that means, and I don't think anyone does with great confidence. But it's certainly, in my mind, a nice option that we didn't really have the potential to consider in much detail before, given the standard moon forming picture of it always being hot as all this material falls down together. And I know there are some papers that say that a shallow magma ocean is good for having deeper sources of garnet forming and certainly getting this thin crust, but I think there's a lot of uncertainty for what the water does and all of the things like that. I can't remember if you asked about volatiles, but I'll talk about that anyway since I've got the chance. Because the picture used to be that the disk, before you make the moon from it, was a really good place to evaporate the volatiles. But I think the recent picture is more that you don't need that so much, and actually just the magma ocean on the surface of the moon after is plenty for getting rid of that. So that would be probably the picture in this scenario as well.
Great, thanks a lot. Very, very thought-provoking.
Right, do we have other questions? If not, oh yeah, so we have a question for Darrell, from Darrell.
Hi, you showed earlier that the traditional model with the Mars impactor didn't quite match all of the properties of the moon. I didn't quite catch at the end with your latest simulations if you are capturing all of those effects? And if not, what changes do you think to the standard simulation could perhaps explain those effects?
Yeah, so I guess in a way it depends how much detail you go into. To me, the problem is that, which is obviously a good thing, we know so much about the moon, but there's also so much that we don't know. So it's very tricky to try and match everything. The big thing that the canonical model does not explain is the composition. You get this debris disk that is almost entirely made of the impactor. And so unless you were lucky and had that impactor being made of very Earth-like material in terms of the isotopes beforehand, it seems unlikely that you would get a moon that looks so similar to the Earth as it does now for the isotopes. So that's the big problem with the canonical model. Though, like I said, there are still discussions of how completely that rules it out or not. With our model, let me phrase this a different way. With the synestia forming and high angular momentum models that propose to completely solve that isotopic problem, they then have all of this extra angular momentum that you need to get away in or around the evection resonance or other mechanisms. And that's, I think, still an ongoing discussion of how likely that actually is. So that could be a problem, or it could work quite nicely, who knows. Same for the other scenarios as well. They all manage to increase the amount of Earth you get in the moon, but with some open questions for whether it causes other issues. So in our model, we are fine with the angular momentum. You can have it higher if you want by having a spinning Earth, since we found that doesn't make a difference. But we can immediately get an orbit and Earth spin that fits with what we see today. And the masses are all fine. The composition is better than the canonical model. Again, I don't think it's fair to say that this solves the problem or doesn't or anything. But it certainly could help. And as I mentioned, there are all of these other bits and pieces that could help explain that as well. And then in terms of the somewhat side topics that most of the impact scenarios don't tend to deal with that much, because it's so many other disciplines that need to be brought in, with the fossil figure, the orbit evolution for explaining the inclination and so on. I don't think, I don't think anyone has paid much attention to starting the moon in a different way like you could here. So I don't know for sure how much that is going to help, but we can also get a similar starting place to a disk accretion model here. So it's not necessarily hugely different, but it opens up some new options. And to actually answer the question of how did the moon form and which of these models is right, I don't think it's going to happen anytime very soon. We're certainly getting good at ruling out some things that really don't work, but the evolution from those millions of years ago to today is a really complicated one. And on top of that, we have so much uncertainty of the initial conditions before the impact, because obviously this wipes out so much of that information. So that was a long answer, but I hope that answers most of what you were asking.
Right, now we have a question from Raj. Go ahead, Raj.
Hi, Jacob. Great talk. Thanks. I was wondering, so in your model, the reason the composition, compositional similarity between our planet and the moon is working out better is in your debris disk. If I get it correctly, the debris disk is made up with more materials from the proto-Earth and less from the impactor, correct?
Well, the satellite itself has. Yeah, so actually that's a good point I didn't mention, is that the outer layers of the satellite, so up to about half of its mass, have significantly more proto-Earth material than the interior, and the debris disk is similar. So if the moon is going to then accrete more, which it might well do, either from moonlets or just viscous spreading from the debris disk, then that would also add some more Earth material on top.
And the debris disk and the outer layer, they are similar in composition.
Yes,
in terms of the ratio of the impactor and the proto-Earth.
Yes, it varies a bit from scenario to scenario. Like I mentioned, we did a whole range of different things here, and we make a bunch of different types of satellites. We even get some with massive cores, as well as the more interesting moon-like ones that I mentioned here. So that does vary, but in general, yes. The main point is that compared with the canonical scenario where the entire impactor is spread out through the disk, here we get to kind of keep a whole load of the impactor trapped deep inside the moon and have another part of it go deep inside the Earth, so that then all of the outer layers and the debris disk can have a lot more Earth material in it.
And maybe it's related to that. So maybe you mentioned it and I missed it. In terms of what was the sensitivity and the result of the sensitivity analysis in terms of what scenarios result in this particular picture you just painted more so than the others in terms of the speed and the angle and the impacted target? So which ones? There must be some sort of a dependence, right?
Yeah, no, it's a very good question. Again, it's a tricky one to answer because of you need to know what distribution of impact angles and speeds you'd expect at the beginning to then decide how this actually affects the likelihood. I think we've gone back and forth of people used to think that a canonical one, which means quite a slow speed, was very likely, and then people were saying it's actually less likely, and now we've got these new ways to lead into that. But this is not a hugely high likelihood thing. There is a range of parameter space. It's not a super fine-tuned thing. You can have a few degrees, and especially a whole bunch of spins can help this happen as well. But it is a fairly small region of parameter space in speed and angle, much like the canonical model, much like the hit and run impacts. A lot of these other models are fairly localized. And I think, yeah, so I don't think we're hugely different here from the other models. It's maybe a little bit smaller. But I guess the main point is that since we only have the one moon, maybe it was unlikely. Obviously, we shouldn't allow that thinking to go too far. But I guess it is something to keep in mind.
Yeah, thanks.
All right, last chance to ask a question to Jakob. And if no, I guess we'll close here. Thanks again, Jakob, for this great talk. And
thank you. And people are obviously welcome to email me at any point if anything does come to mind later. But thanks for having me.
That was our pleasure. And yeah, so see you everyone in 2 weeks for the next seminar, which will be given by Karin Oberg.